This podcast is on polynomials, their properties, and graphs. Earlier this year we discussed quadratic equations, ax squared plus bx plus c equals 0, and how they were solved using the quadratic formula. The part ax squared plus bx plus c is also called a quadratic polynomial. If we remove the 0 and we replace it with f of x or y, we get what is called a quadratic function. Y equals ax squared plus bx plus c. Now, since the expression has x's and y's, we can graph it in an xy coordinate system. Again, the part of the expression ax squared plus bx plus c is called a quadratic polynomial. And the components, the terms in this three-term quadratic polynomial are called monomials. But not every term in every expression is a monomial. So let's take a look at that. What do we mean by a monomial? A monomial is a term, so it's a product, in which the power of x is a non-negative integer. So if we take a look at some examples of monomials, the first term I have here is 4x cubed. The 3, the power of x, is called the degree of the monomial. And it's a monomial because 3 is a non-negative integer. In the second example, the 4 is to the negative 1, which is a negative integer, but we don't care about that. We're interested in the power of x. If the power of x is a non-negative integer, this is a monomial, so this simply means 1/4 x squared, and it is a monomial. And a polynomial you get by just adding monomials together. My last example of a monomial is just the single number 6. And the reason that's a monomial is that you can think of it as 6x to the 0 power. 0 is a non-negative integer, so this satisfies the definition of a monomial. So if we add those together, we get a polynomial with 3 terms. Now let's look at some terms that are not monomials. If I look at the term 4x to the 1/2, that's not a monomial because 1/2 is not an integer and it's the exponent of x. If I look at the second one, 4x to the -2, -2 is not a non-negative integer, so that's not a monomial. And if I look at 4 over x squared, 4 over x squared is 4x to the -2, so that's just like that was a negative exponent. So when you talk about having positive integer exponents, that is when the x is in the numerator. Now, what do we mean by the degree of a polynomial? Well, each monomial has a degree, and it's its power of x. This monomial has the degree 3. This monomial is of degree 2, and this monomial 6 is of degree 0 because the power of x was 0. Now, the degree of a polynomial is just the degree of its highest degree monomial. So if I look at the polynomial in example 1, its highest degree monomial is degree 5, so we say the polynomial has degree 5. If I look at the second polynomial, its highest power of x is not in its first term, it's in its second term, x to the 4th. So we would say this polynomial function, the polynomial part, has degree 4. Now, let's take a look at some of the properties of these polynomials because we're going to be graphing them and we want to know what their graphs are going to look like. The first property we want to talk about is that polynomial graphs are smooth and continuous. Here I've graphed this polynomial 1/2 x cubed minus 2x squared plus 2. Notice first off how smooth the graph is. Nice big sweeping curves, nothing coming to a jagged point. The degree of the polynomial is 3 because that's the power of its highest power monomial. It has 3 zeros, which agrees in this case with the degree, and it has 2 terms, which is 1 less than the degree. That is the degree of 3. 3 minus 1 is 2. We're going to find that these patterns that we've observed here holds up as we look at different polynomial graphs. Off to the left here, I've shown a couple of graphs that are not polynomials. The first is not a polynomial graph because it comes to this sharp point. The second is not a polynomial graph because it's not continuous. There's a big break in it. Continuous means that, like this curve, you have to be able to draw it completely without picking up your pencil. If there's a big gap in it, it is not a continuous curve. And then down at the bottom of the sheet, we have some graphs of polynomials. I'd like to bring your attention to something called the end behavior. As you move to the left or move to the right, what's happening down here on the end? And these have an end behavior where both of the ends are going to negative infinity. In the second graph, the left end is going to negative infinity, the right end is going to positive infinity, etc. They're all smooth, there are no breaks. Those are all polynomial functions. Now we want to talk about their graphs. The first polynomial I've graphed here is the polynomial y equals 1/2. Got to get this centered right in the sheet here. Y is equal to 1/2 x plus 1. This is a polynomial of degree 1. I want you to notice that it crosses the x-axis in one spot. And we have a rule that corresponds to that. It says the number of zeros in a polynomial has to be less than or equal to its degree. A zero is a point where y equals 0. So this has one value of x where y is 0 corresponding to degree 1. The second thing I want to point out is that it has 0 terms. And that leads us to a second rule. It says the number of turns is less than or equal to the degree minus 1. The degree is 1, so the degree minus 1 is 0. This can have 0 turns, and that's the way it is. Of course, that's a pretty flimsy example, so let's go on to see if these rules hold under a more complicated polynomial. So I've written out this graph of this really long polynomial here. I got this graph off of my graphing calculator. But when you factor that out, it's actually pretty simple. It's x plus 2 cubed times x minus 1 squared. Now, a 0 of a polynomial is a value of x that makes y 0. So you can see here if x was negative 2, that would be a 0. And over here, if x was 1, that would be a 0. And you notice in the graph I have two spots where the graph hits the x-axis, and that's negative 2 and 1. These 2 points right here are my zeros of my polynomial. Now, this particular 0, negative 2, occurs in a product 3 times. So we say it has multiplicity 3. And the 0 x equals 1, we say has multiplicity 2 because we have 2 factors of x minus 1. So y equals 0 when x is negative 2 and x is 1. So x is negative 2 and x is 1 are called the zeros of f of x. Negative 2 has multiplicity 3, negative 1 has multiplicity 2. Let's take a good close look at their graph. For the 0 of multiplicity 2, look how the graph behaved. It came up and it started to flatten out like it was going to turn, but then it turned back and went right through the x-axis. Now look at how that differs from the 0 of multiplicity 2. One occurred twice. It came down and started to flatten out, but it did turn and go away and never did cross the axis. And so we come up with this rule for the multiplicity of zeros. It says when the multiplicity of a 0 is even, the graph bounces off the axis. So here's our 0 of multiplicity 2. The graph bounced off the axis. When the multiplicities of a 0 is odd, the graph flattens but crosses the axis. So here was our 0 of multiplicity 3. The graph came up, it kind of got flat, but then it crossed over the axis. Notice also number of zeros 2, that's less than or equal to the degree, which was 5. Number of turns 4, that's actually equal to the degree minus 1. So the rules we saw for the first simple graph up here are holding for the more complicated graph. Now the last thing I want to talk to you about are called end behaviors, and that's what happens at the right end and the left end of a graph. In the first graph I'm looking at, it's y equals 1/2 x squared plus 1. This is the graph. Again, I got it out of my graphing calculator, and I wanted to show it to you so you could investigate how you determine how a graph will behave at its end. And what you do is, to determine an end behavior, you look at the highest degree monomial. So in this case, to determine the behavior at the ends, I want to look at this monomial 1/2 x squared. Now what happens as x moves off to the left? That is, as x goes to negative infinity. That's what this symbol means. X arrow negative infinity. X is moving to the left. It's going to negative infinity. So what's happening to this monomial? Well, it's 1/2 of a negative squared. A negative squared is a positive. Half of that is a positive. And that's why that is going to positive infinity. That is, it's going upward to infinity. Well, what happens for the right end behavior? Well, as x goes to the right, as x goes to plus infinity, we get 1/2 of a plus squared for our first term, which a plus squared is a plus, half of that is a plus, so we're going to plus infinity. Now contrast that with the second graph. Here's the highest power monomial of the second graph. This is the monomial that will determine our end behavior. What happens as we move to the left? That is, as x goes to negative infinity. Well, we get 1/2 of a negative cubed. A negative cubed is a negative. Half of a negative is a negative, so we're going to negative infinity. And you can see right here the graph is heading downward to negative infinity as we go to the left. Well, what happens as we go to the right? Well, as we go to the right, we're going to positive infinity, so we're going to be cubing a positive, which gives us a positive. Half of that will still be positive, so we're going to positive infinity, and that's what shows in the graph. Let's take a look at one more. In the last one, we have this is our highest power monomial. It's power 4. What happens as we go to negative infinity? Well, we get a negative to the fourth. A negative to the fourth is positive, so we're going to positive infinity, and you can see here by the arrow that we're going to positive infinity. Well, what happens as we go to the right? Well, then x is going to positive infinity, so we have a positive to the fourth. So that's going to go to positive infinity, which tells us y is going to positive infinity, and you can see from the graph that it really was going upwards, which is to positive infinity. One last note. When the power of x was even, like in graph 1 and graph 3, the two end behaviors were the same. So when your biggest power monomial has an even exponent, you only have to check one end behavior. The other end behavior will be the same. Now we looked at two graphs that had odd powers for their biggest power. This graph, notice the end behaviors. On the left end, it was going to negative infinity. On the right end, it was the opposite. Go back to our big graph up here. That again, its biggest power was the fifth power, an odd power. Look at its left end behavior. It's going to negative infinity. Its right end behavior is going to positive infinity. So we can draw a conclusion about this. And the conclusion is, if the degree is even, the end behaviors are the same at both ends. So you only have to look at one end behavior. If the degree is odd, the end behaviors are opposite at each end. So again, you only have to look at one. If you determine that on the right it's going up, then on the left it will be going down if your degree is an odd degree. Now in our next podcast, we'll learn how to take these little rules and actually use them to graph polynomial functions, and that completes our podcast.